Okay, this is the video for Test 1 for Math 136, version A review. For the first problem, we have a radical that we need to simplify. Since these pieces under the radical are all multiplied together, we can break this up actually into 3 separate radicals and look at each one individually. If they were added or subtracted together, we couldn't do this, but since they are multiplied, we can. So this first part, the square root of 75, anytime we have to take the square root or cube root or any root of a number, I think it's helpful if we make ourselves a prime factor tree. Okay, so 75, we need to think of any two factors that when they multiply together, they give us 75. We could do 3 times 25. And then 25 is 5 times 5. And now that we have prime numbers at the end of every row, that's our prime factorization. Since we are looking for a square root that has an index of 2, so that means we are looking for pairs of numbers that can come out of the radical. Okay, the pair of 5s comes out of the radical. The square root of 5 times 5 is just 5. So that pair, when it comes out of the radical, becomes just a single 5. And then the 3 has to stay inside. Here for the square root of x to the 12th, remember square root has an index of 2, like we just said, so we can take that exponent and divide it by 2. That means after we take the square root, we are going to have x to the 6th. If we had a remainder, that would tell us how many x's needed to stay inside the radical. Since this one divides out evenly, they all come out of the radical. Same thing here for the square root of y to the 20th. 2 goes into 20 10 times, so this is equivalent to y to the 10th. Okay, remember these were all factors, they were all multiplied together, so when we put our final answer together, we would write this all would be multiplied together. 5x to the 6th, y to the 10th, times the square root of 3. Okay, our next one, we are simplifying another radical. This one is a cube root instead of a square root. So we're going to start again by making a factor tree for 108. 108 is 2 times 54. And you can use a calculator to help you with this if you need to. 54 is 2 times 27. 27 is 3 times 9. 9 is 3 times 3. So there are our prime factors. If we multiply those all back together, we would get 108. So this time we have an index of 3, a cube root. So we're looking for groups of 3. Here's one group of 3. So that means the cube root of 108 is equal to 3. That comes out. The two 2's have to stay inside, and 2 times 2 is 4. So there is our simplification of cube root of 108. For x to the 8th, we'll do the same little dividing trick we did in the last problem. So 3 goes into 8 2 times, but it's not even this time. We have a remainder of 2. So our answer, that tells us how many can come out of the radical. So x squared comes out. And our remainder tells us how many have to stay inside. So we also have x squared comes in. Okay, same thing for the cube root of y to the 10th. 3 goes into 10 3 times with a remainder of 1. So that means that 3 can come out and 1 stays inside. Again, we want to put all these pieces back together again to get our final answer. Again, we build our answer through multiplying. So outside of the radical, we have 3 x squared y cubed. And inside the radical, don't forget that index. Sometimes people forget and drop that. We have 4x squared y. There is our final simplified answer. Okay, number 3, simplifying with exponents again. So here we have a negative fractional exponent. So kind of two things we have to deal with in that exponent. And a lot of times people want to jump in and take that exponent and apply it to every factor. But for these problems, a lot of times it's going to be easier if you simplify what is in the parentheses before we ever even look at that exponent. So ignore the exponent for a minute. Just look at what's inside the parentheses. Negative 24 divided by 3. Well, that can be simplified. That's negative 8. We have x to the 34th on top, x to the 61 on the bottom. Remember, when we're dividing, we subtract those two exponents. We end up with x to the 27 on the bottom. And the y's, there aren't any y's to be canceled, so that just stays. Okay, now we've gotten the expression inside the parentheses as simplified as it can be. So when I have a negative exponent and a fraction exponent, I usually take care of that in 2 steps. The fact that that exponent is negative means that we need to flip the whole fraction upside down. Once we do that, I can now write that as a positive exponent. So all I did, take the x to the 27th and move it to the top, take the negative 8y to the 9th and move it to the bottom. And when I do that, that exponent goes from negative to positive. Notice this negative 8, that does not change. That's a negative number, not a negative exponent. That just stays behind. And now, finally, we can apply that 1/3 exponent to every factor that we have here. And these are all, they come out nice and even. That's nice. 27 times 1/3 means we have x to the 9th on top. Negative 8 to the 1/3, that's the same thing as saying the cube root of negative 8, which is negative 2. And then y to the 9th to the 1/3, 9 times 1/3 is y cubed. So there is our final answer for number 3. Okay, for number 4, our directions ask us to factor completely. If the polynomial cannot be factored, we write that it's prime. So there are a few different techniques for factoring a polynomial like this. I will show you one of those, and then you can maybe have another method yourself. Whenever there's something in front of the x other than 1, a lot of times we do this little trick where we take 3 times negative 28, which is negative 84. And then we have the x coefficient, which is just 17. So what we are looking for now is 2 numbers that will multiply together and give me negative 84 and add up to give me 17. And it might take a little thinking. You might have to use your calculator and do a little trial and error, but that's going to be a negative 4 and a positive 21. Okay, once you have those 2 numbers, what you do with them depends on what technique you're using. So some people do the AC method and factor by grouping. Some people do bottoms up. I'm just going to go ahead and do the factoring by grouping. So what we do is we write down the first x squared term, but that 17x, we split that into 2 terms, minus 4x plus 21x, and then the minus 28 just stays. And then we go ahead and apply factoring by grouping to this polynomial. So from these first 2 terms, we can pull out an x, and what's left behind is 3x minus 4. From our second 2 terms, we can pull out a 7, and what's left behind is 3x minus 4. Since this matches this, that means factoring by grouping worked. And our final factoring step is to pull out that 3x minus 4, and what's left behind is x plus 7. There is our factored polynomial. Okay, next one is another factoring problem. Oops, sorry about that. This time we take a look. We only have 2 terms, so it's not going to be the same kind of problem as last time. Sorry. When we have 2 terms, first thing we want to think about maybe is there a greatest common factor? No, 27 and 64 don't share any common factors. So then we want to think about, does this have any of our special factoring formulas that would apply here? And you might notice 27 is a perfect cube, and so is 64. So we are going to apply our difference of 2 squares formula, which looks like this. A cubed minus b cubed. Oops, sorry. is equal to a minus b times a squared plus ab plus b squared. Okay, to figure out what a and b are in our particular problem, we just take the cube root of each one of these terms. So the cube root of 27x cubed, that means that our a is going to be 3x, and the cube root of 64 is 4, so our b is 4, and then we apply our formula. So our answer is going to be 3x minus 4, that's a minus b, times a squared, don't forget to square both the 3 and the x, plus ab plus b squared. There is our final answer. The next one we notice is also just two terms. So we look, is there a greatest common factor here? There's not. So does one of our special factoring formulas apply? And this one, similar to the last one, this one is the sum of two cubes. So a cubed plus b cubed. The formula we need here is a plus b, a squared minus ab plus b squared. And this time a is the cube root of 8y cubed, which is just 2y. And b is the cube root of 125, which is just 5. So if we fill in our formula, a plus b is 2y plus 5. A squared is 4y squared minus a times b. So there we get 10y plus b squared plus 25. And one more factoring here, another polynomial. So again, we would look for a greatest common factor. There is not one. Right now at this point in our class, the only trick we have if there are more than 3 terms and there's no GCF is to factor by grouping. So that's what we want to try here. If we, oops, sorry, it jumped around on me. There it is. So if we split this into 2 pieces, the 2 terms in front of the vertical line there, we see what do they have in common. And the GCF there would be 25x squared. When we factor out 25x squared, 50 divided by 25 is 2. X cubed divided by x squared is just x. 75 divided by 25 is 3. And we took both the x squareds away, so that's gone. And then for the 2 terms that come after that line, negative 72x and negative 108, might take a little trial and error, but we would find that they do have a common factor. It is 36. Anytime this first term is negative, you're probably going to want to go ahead and factor out a negative number. So negative 72x divided by negative 36 is 2x. And then negative 108 divided by negative 36 is plus 3. So we can see that factoring by grouping worked because we got matching factors there. So when we pull that out front, what's left behind is 2x squared minus 36, which it looks like it's factored. Oh, sorry, 25, not 2. It looks like it's factored, but we're not actually done yet because this piece can be factored again. That's the difference of 2 squares. So our final factorization would look like this. Okay, for number 8, we want to divide a couple rational expressions, okay? When we are dividing fractions, the one thing you want to remember is that the division of fractions is the same as multiplying by the reciprocal. So that's what we're going to be doing here. That means we're going to take this second piece and flip it upside down and change this into a multiplication problem. The other thing we want to do anytime we're dealing with rational expressions like this is we want to try to factor everything because we want to simplify as much as possible. So this first polynomial up top, x squared plus 4x plus 3, we can factor that. 3 can only be 3 times 1. Since we need a 4x in the middle, those both need to be positive. Then we look at our denominator. That's another trinomial that factors. 18 could be 1 times 18. Sorry, I keep hitting things with my hand. Ignore that. 18 could be 1 times 18, 2 times 9, 3 times 6, but the only way to get that 9 in the middle is with both a 3 and a 6. If we want a negative 9 and a positive 18, those both have to be negative. Okay, then I'm going to go ahead and flip the other one. So to get the reciprocal, the x minus 6 goes up top. And then we can factor that final polynomial. We need factors of negative 12 that are going to give a difference of negative 1. So a 3 and a 4, with the 4 being negative and the 3 being positive. Then when we multiply fractions, remember when we multiply two fractions, we just multiply straight across the top and straight across the bottom. So we can go ahead and cancel any common factors here. Okay, so canceling common factors, that means the x minus 6 can go away, the x plus 3 can go away, and then we're ready to write out our final answer, x plus 1 up top, and x minus 3, x minus 4 on the bottom. Sometimes people distribute that. I would say leave it factored. There's no need to take that extra step. Okay, number 9. Now instead of multiplying rational expressions, we are adding them. In order to add two fractions, we need a common denominator. So before we even get started, let's just figure out what that least common denominator would be between those two fractions. And we can kind of consider the numbers, the coefficients, and the variables separately. The least common denominator between 7 and 5 would just be 35. They don't have anything in common. X cubed and x squared, if we're talking about the LCD there, that would be x cubed. You always take the highest exponent. Y squared and y to the 4th, that would be y to the 4th. So there's our LCD. So before we can do any adding of fractions, what we need to do is we need to do some work to get each one of these fractions to have that LCD, that same denominator. Okay, so what would I have to multiply this fraction by in order to get that least common denominator that we're going for? Well, 7, I'd have to multiply that by 5. So if I do it on the bottom, I got to do it on the top too, so I don't change the value of the fraction. X cubed is in my LCD. I've already got an x cubed in my denominator, but my LCD has a y to the 4th. I only have a y squared, so I need another y squared. Okay, so that takes care of my first fraction. The second one, again, what do I have to multiply that by to give it the common denominator I'm looking for? This time I got to multiply the 5 by 7. X squared is what I have. X cubed is what I want, so I need to multiply the top and the bottom by x. Y to the 4th is what I have, and that's what I want for my LCD, so that's it. Okay, so again, before we add, simplify these two. So these two, when I multiply those together, I get 20y squared on the top and 35x cubed y to the 4th, which is that common denominator I was looking for. And when I multiply these two fractions, I get 2 times 7, 14x on the top, and 35x cubed y to the 4th on the bottom. Don't cancel anything in common. We did that on purpose to get this common denominator, so we just add those two numerators and put it over our common denominator that we just found. And there's our final answer. Number 10, similar, except we are subtracting the fractions instead of adding them. So again, no matter if you're adding or subtracting, we need to figure out what the least common denominator is. Before we can do that, we probably want to factor each one of these denominators. So this first one factors into x minus 4, x plus 4. The second one is a trinomial that's going to factor. I need a product of 20 and a difference of 9. So that's going to be a 4 times 5. And if I need that to be a negative 9, those both need to be negative. Okay, so of these two denominators, my LCD has got to have an x minus 4. It's got to have an x plus 4. And it also needs an x minus 5. That's what I need the bottom of each fraction to look like. So my first fraction already has the x minus 4 and x plus 4. So what I need to multiply in here is the x minus 5 on the top and the bottom, so I don't change the value. My second fraction has the x minus 4 and the x minus 5, so this time I need to multiply in the x plus 4 to get that common denominator. Okay, so now I'm ready. I'm going to kind of simplify and put these together all at once. Actually, I'll write out one more step. So 3x minus 5 minus 7 x plus 4 over x minus 4 x plus 4 x minus 5. And then we've done the subtraction, but we want to go ahead and simplify the top. We'll distribute on both of those. Oops, sorry, not 28x, just 7 minus 28. And then finally combine any like terms. So 3x minus 7x leaves us with negative 4x. Negative 15 minus 28 is negative 43, all over that common denominator. One common mistake I see here, a lot of times people will skip this step, which is fine, but you need to be careful that you are, when you do this distribution, that you are distributing a negative 7, okay, because it becomes a minus 7x and also a minus 28. That's a really common error that I see on a problem like this. Okay, number 11. And this time we have a complex fraction, fractions within a fraction. There are two different ways you can handle a problem like this. I'm just going to show you one of them, and that is I'm going to take this original expression, multiply the top and the bottom by the same thing. I'm going to multiply the top and the bottom by the least common denominator. We have a 1 over x on the top and a 1 over x squared on the bottom. So the LCD would be x squared. So I multiply the top and the bottom by x squared. Okay, so we need to distribute that up top. We get 4x squared minus x squared over x. On the bottom, we get 16x squared minus x squared over x squared. And then we can do some simplifying. X squared divided by x is just x. X squared divided by x squared is 1. And if we continue, we can factor the top, pull out an x. We can also factor the bottom, because that's the difference of two squares. And you can see the reason we didn't stop here is because now we do have a common factor to the top and the bottom, so those two can be canceled. And our final answer looks like that. Okay, number 12. This is the one I always call in my class the big factor. Okay, students get really kind of nervous about this problem, but I'm going to try to convince you that it's not really so bad. Okay, really, this is just two terms that have a GCF. Okay, so notice this plus sign right here. That's an important one. It's the only plus or minus that's not inside a set of parentheses. And that splits our problem up into its two terms. There's the first term, and there's the second term. Okay, so just like a basic GCF problem, we are looking, what do those two terms have in common? Well, right away I can see they both have an x minus 5. So that's going to be part of my GCF. I'm going to pull that out front. Okay, so that comes out front. Well, how many of them? X minus 5 to what power? We have x minus 5 to the 9th, and we have x minus 5 to the 8th. You can only pull out the smallest exponent. Okay, Then next up, we see that they both have a 2x minus 3. So that means that's going to be part of our GCF that comes out front. Again, how many? We have 2x minus 3 cubed and 2x minus 3 to the 4th, so we can only pull out the smallest exponent. So the only thing we haven't addressed yet is this 2 and this 4. So 2 times 4, that means this term really has a coefficient of 8. And then here we have a 3 and a 6. 3 times 6 is 18, so that term really has a coefficient of 18. 8 and 18, what do they have in common? What would be the GCF between those two numbers? That would just be a 2. Okay, so that is our GCF. Now we need to write our leftovers. So let me kind of clear this out so we can look at this again. Okay, so from our first term, we had x minus 5 to the 9th. We factored out 8 of those. So there is one x minus 5 left behind. Took care of that. We had 2 times 4, which is 8. We factored out 2. So that means there is still a 4 left behind. That takes care of those. And then we had 2x minus 3 cubed. We took out all 3 of them, so none of those are left behind. Okay, it's very important not to lose that sign. There's still a plus between these two terms. Okay, we had a 3 times 6, that's 18. We factored out a 2, so there is a 9 left behind. X minus 5 to the 8, we factored out all of those, so they are all gone. And 2x minus 3 to the 4th, we factored out 3 of them, so there is 1 left behind. Okay, leave that GCF out front alone and just simplify what we have in the parentheses here. So we want to distribute the 4, and we want to distribute the 9, and then combine any like terms. 4x plus 18x would be 22x, and negative 20 minus 27 would be minus 47. And then we want to go ahead and make sure, I didn't write it every time, but make sure you still have that GCF out front. So there is our final factorization. Okay, now we're going to move into solving some equations. This first one is a rational equation, and it's a special case of the rational equations because there's just one fraction on each side of the equal sign. Anytime we have that case where there's just a single fraction on the left and a single fraction on the right, we can use one of our quick and easy tricks, and that is we are going to cross multiply. So we are going to go from down here to up there, so we get 6 times 3p plus 4, and then we multiply the other way also. We get 3 times 2p minus 3. Don't lose your equal sign. It was an equation. It still needs to be an equation. You can see that once you cross multiply, it's no longer a rational equation. This is just a basic equation that we can solve. We'll go ahead and distribute on both sides. And then we just need to move around to solve. Once we do that, 18 minus 6 is 12p equals negative 9 minus 24 is negative 33. Divide both sides by 12. We get p equals negative 33 over 12. Be careful, you're not finished there. That is a fraction that can be reduced. Both of those numbers are divisible by 3. So there's our final answer. Okay, the next one up is another rational equation. This time we do not have a single equation on the left and the right, so we can't cross multiply, okay? So what we want to do here, again, is we want to use the least common denominator. So let's figure out what that is. We need to factor this polynomial here. That would be 6 times 1, 6 plus 1 will give me 7. Okay, so our LCD for all 3 of these fractions would be x plus 6, x plus 1. So what we want to do here is we can't solve this equation with those fractions in it. We want to get rid of the fractions. Okay, in order to get rid of the fractions, we are going to multiply the entire equation by this LCD. Okay, so I'm going to write it out kind of long ways. Okay, we're going to multiply everything by the LCD. Okay, so you can see we're going to have to distribute to all three parts of the equation. When I multiply this first fraction by x plus 6 times x plus 1, you can see that the x plus 6 is going to cancel, and we're just left with 1 times x plus 1. When we distribute it to the second term, it's the x plus 1s that cancel, and we're left with 3 times x plus 6. And then on this last term, both cancel, and we don't have any left behind at all, just the 2. I didn't need that 1 out front, obviously. This is just x plus 1. We distribute the 3. And then go ahead and gather up your like terms. Subtract. You get 4x equals negative 17. Divide both sides by 4. We do want to double check. I actually forgot to do it in the last example. Take a look at the solution. When we plug that in for x, does that give us 0 in any of our denominators of our original equation? In this case, it does not, so that answer is okay. But you always want to check that when you have fractions in your original equation. Okay, word problem. This is a work type problem where we have sometimes 2 people or 2 pieces of equipment doing a job, and then how long it takes for them to do that job together. So in this case, we have 1 pipe can fill a pool in 4 hours, a second pipe can fill the same pool in 7 hours. If both pipes are open, how long will it take to fill the pool? Okay, so pipe number 1, first I'm just going to write down the information they told us. Pipe number 1 takes 4 hours to fill the pool. Pipe number 2, it said, takes 7 hours to fill the pool. And when you open both pipes, or when they're working together, that's what we don't know. We're going to say x hours. It's not going to be 4 plus 7 equals 11. Obviously, it wouldn't take more time if both of the pipes are turned on. So the trick to a problem like this is we don't want to know how long it takes to do the job. We want to know how much of the job they can do in 1 unit of time. Okay, in this case, it's in 1 hour. Okay. So if pipe number 1 fills the whole pool in 4 hours, that means in 1 hour, it can fill 1/4 of the pool. If pipe number 2 can fill the entire pool in 7 hours, in 1 hour, it would fill 1/7 of the pool. And if both pipes are turned on and working together, it could fill in 1 hour 1/x of the pool. That's our unknown. Now, when we put it in this terms and how much work can be done in an hour, these are now additive. So we can write an equation. That means that pipe 1 plus pipe 2 is going to be how much they do together in 1 hour. And you can solve this a couple different ways. Maybe we just get a common denominator on the left. So 1/4, if we multiply by 7/7, that becomes 7/28. 1/7, we multiply by 4/4, that becomes 4/28. Sorry, 1/x. So 11/28 equals 1/x, and now we can cross multiply. That means 11x equals 28, or x equals 28/11. In this case, we want to give a decimal answer. It asks us to round our answer to the nearest tenth. So 28 divided by 11 is about 2.5. It would take about 2.5 hours for those 2 pipes to finish the job working together. And now our final problem is a mixture problem. We've got a solution containing 9% concentration of an acid is mixed with a solution containing 5% concentration of an acid to get 100 milliliters of a solution containing 8% concentration of the acid. How many milliliters of each solution is needed? Okay, I know sometimes people struggle with these kind of problems, but it's really just a matter of organizing the information that they give you, reading through the problem, figuring out what we're doing. So we are mixing whatever this solution number 1 is, we're going to mix it together with some solution number 2 to get this mixture, this final concentration, okay? So the first thing I want to take a look at is what is the concentration of each one of these ingredients, okay? Solution number 1, it tells us right there, has a 9% concentration. The 9% concentration is mixed with a solution containing 5% concentration. So that's the concentration of our second solution. And we mix those together to get 100 milliliters of a solution containing an 8% concentration. So just sort those numbers, okay, the concentrations of each. Then we want to know the amount of each of these ingredients. We read through, the only amount given in the whole problem is this 100 milliliters. We need to figure out where that goes here. It turns out that's going to be our resulting mixture. That's the 8%. So the 100 mLs have to go over here. We don't know how much of solution 1 or how much of solution 2. Those are the two variables that we're going to solve for. Okay, so I think it's a good idea to put your information in a table first. From that table, we get 2 equations. The first equation just comes from the amount of each ingredient right here. So our first equation is just x plus y equals 100. Okay, if we mix 2 liquids together and the result is 100 milliliters, when we add them up, that's got to equal 100. Our second equation comes from multiplying. So basically, it's the amount of active ingredient in each. We multiply the concentration by the amount for each one of these. Okay, so 9% times x. Make sure you change that to a decimal when you write it in your equation. Plus 5% times y equals, and don't forget, don't just put a 100 over here, don't just put an 8% over here. We've got to multiply those two together too, 0.08 times 100. So at this point, hopefully we can solve this. We have 2 equations and 2 unknowns. You can solve it by substitution or by elimination. This one I happened to do by substitution. I took this first equation and solved it for x. And then I took that expression and plugged it in place of x in the second equation. So we end up with 0.09 times 100 minus y plus 0.05 times y equals 0.08 times 100 is actually just 8. And then we want to distribute that 0.09. Combine our 2 like terms. Subtract the 9 from both sides. And then divide both sides by that negative 0.04, and we get y equals 25. Okay, this is a word problem, so we want to label our answers. This is the amount. So it's 25 milliliters, and y was of the 5% solution. And we also need to give x because the question asks how much of each. Okay, we can get x by looking up here at our very first equation right here at the top. If x plus y is 100 and y is 25, that means x has got to be 75 milliliters, and that is of the 9% solution. And that's it.